China, a stunning new landmark rises above the clouds. A steel and concrete giant with the waist of a supermodel. Rising over half a kilometer into the sky, the Canton Tower is the tallest tower on Earth. It's a true symbol of China's growing industrial power and a marvel of engineering. This wonder of the East wouldn't be possible without four key inventions found in a series of landmark towers. One by one, traveling up the scale, we'll reveal the incredible stories behind these structures and the innovations that allowed them to soar higher into the sky. Four ingenious leaps forward, from big to bigger, into the world's biggest. Guangzhou, southern China. This ancient city is the third biggest in the People's Republic. And like the rest of the country, it is booming. New buildings rise up every day. But there's one that really draws the crowds. The city's new television tower. Soaring to a record height of over 600 meters, the Canton Tower has become an icon for Guangzhou's ambition. It seems everyone wants to get to the top. Today, the tower's architects, husband and wife team Mark Hemel and Barbara Kout, have flown in from Holland.
When I saw the tower for the first time, it was a very happy moment. You see something in its full height, the way that it fits into the city and in the skyline. It was a good moment for me.
It's wonderful to see it like as an end result. It looks very beautiful, and it's also nice to see that it has been embraced by the Chinese.
Mark and Barbara want to see how the Chinese construction team has transformed their design into reality. The Canton Tower is packed with features designed to thrill. Panorama decks with breathtaking views. Fine dining in revolving restaurants. And when complete, a rooftop ride for the adventurous visitor. It has taken only 3 years to build this tower. An amazing achievement.
One of the main difficulties with this tower was the fact that it's so very thin and so very tall. So a combination of tall and thin means that it has to have enough strength in order not to be so flexible that you would actually feel it moving while you were at the top.
Making a tall tower stand up is a huge engineering challenge. To understand how the Canton Tower can soar so high, we need to travel back in time. In 19th century America, the city of Washington wants to build a grand memorial to a founding father of the nation. Their daring plan is for a stupendous stone tower, taller than any other structure on Earth. By 1836, Washington, D.C. is growing rapidly. And right in the center of the capital, a group of citizens are planning to build a memorial to their first president, George Washington. Their grand plan is to ship in stones from all over the United States and assemble them into a slender stone needle. This tower will not just be taller than all the cathedrals of Europe and the Great Pyramids of Egypt, it will be the tallest structure ever built. The ambitious project relies entirely on donations, and the fundraisers are in a hurry to get going, as geotechnical engineer Jennifer Nix has discovered.
They wanted to get the foundation up where you could actually start the shaft construction so that people, the Americans, could see what they had been donating their money for.
In 5 years, the monument rises 50 meters above its foundations. Then, in 1861, the country plunges into civil war. Funds dry up, and for 20 years, not a stone is laid.
A lot of people thought it was an embarrassment to the country to have just this stub. I think it was called just a chimney stack.
To restore national pride, the government summons one of its top military engineers, Lieutenant Colonel Thomas Lincoln Casey. When he arrives to inspect the site, he's in for a shock. The tower hasn't even reached a third of its height, but it's sunk over a meter into the ground and is leaning to one side. An exploratory tunnel dug down to the foundations reveals the problem. The tower sits on a layer of soft clay and sand. This makes the foundations extremely unstable. If Casey carries on building, the world could have a new leaning tower. Worse, no tower at all.
People doing the original foundation saw this soil type and thought it was going to be strong enough to resist the foundation. But as you can see, I'm just pushing with my hand pressure. Nothing very strong. I haven't lifted that many weights. But just with that, you can see I've already compressed the sample, so you can imagine the settlement of the monument itself with the original foundation.
The leaning stump weighs 30,000 tons, so fixing the foundations is a mammoth job.
Casey had to find a way to level the monument, correct the tilt that was there. So he had to find a way to lower one side, essentially dig out a little bit more earth on one side in order to get the monument level and straight again.
Casey plans to expose the foundations of the stump. He'll remove some soil on one side to swing the monument back to the vertical. Then he'll dig a series of tunnels under the foundations that reach down to a firm layer of clay and fill them with concrete. Finally, large buttresses will connect the old tower to the new foundations. Only then will it be safe to complete the monument. At least that's the plan.
You had to be very careful. You didn't want to crack the existing stone. As workers were digging the trenches and filling it with concrete, he was monitoring the settlement. So if he noticed it started tilting one way or the other, he would put more concrete depending which way it needed to help prop it up.
Casey's plan works flawlessly. The new base is rock solid. And 36 years after it was started, the Washington Monument finally reaches its full height. But the foundation fiasco has left its mark.
you can see different colors on the monument because it took so long to continue construction. The stone that they got wasn't exactly the same.
Thanks to Casey's work, the Washington Monument is a massive success. By 1888, around 55,000 visitors climb it every month to proudly stand on the tallest structure in the world. In Guangzhou, the Canton Tower will be over 3 times as high and heavy as the Washington Monument. This steel and concrete colossus needs extremely strong foundations. And just like in Washington, there's a problem with the location.
There's a river alongside here, very close, so there's a lot of water pressure onto the excavation.
Engineers must build the Canton Tower's foundation in 2 parts. They'll support the concrete core on a thick concrete base set directly into the bedrock. To anchor the tower's outer steel structure, the engineers must dig deeper into the ground. Workers excavate a series of shafts around the central core. They'll line them with concrete rings as they dig, to stop the soggy soil falling into the shafts. Once they reach the lower bedrock, they fill the holes with concrete and finally top them with a concrete ring to tie them to the heavy steel columns.
For every column there's a column pile going down into the till bedrock that's about 20 to 40 meters deep, and they're 4 to 5 meters in diameter. They were dug basically by hand with just a little drilling and like some shovels and so on, yeah.
Building the 30-meter deep foundations of the Canton Tower takes a whole year. To raise the tower itself 610 meters off the ground in only 2.5 years requires another leap in construction technology. Back in 1884, the Washington Monument proves that stone towers can be tall if their foundations are strong. But as towers grow ever taller, stone is pushed to the limit. To build a tower nearly twice as tall as the Washington Monument, engineers in France turned to a revolutionary method of construction. In 1889, the city of Paris is to host the World's Fair. To dazzle the visitors and show off her industrial power, France holds a competition to build a tower over 300 meters high. The tallest tower on Earth. An engineer named Gustave Eiffel submits a radical design. Eiffel has spent years building iron bridges, and he thinks that metal is the perfect material for a tall tower. Eiffel's vision is to build his tower like a vertical iron bridge. He wants to rivet thousands of metal strips together into sections, which he will assemble into 4 gigantic legs. Then he'll connect the legs to one another so he can build a level platform. On top, he'll assemble a huge metal spire over 300 meters into the sky over Paris. But Eiffel's design creates an outcry. It's seen as ugly. A metal monstrosity on the face of a beautiful city. The people of Paris favor a rival design made of masonry, called the Sun Tower. The two tower designs divide Paris in a battle of stone versus metal. Under threat, Eiffel goes on the offensive. A stone tower 300 meters tall, he claims, is impossible to build. Over 100 years later, engineering analyst Carl Brooks puts Eiffel's claim to the test.
We've had to digitize the sketch, set up a set of equations to calculate stresses and strains and so on.
Carl's team has rebuilt the Sun Tower brick by brick on a computer to find out if it could have stood up.
This is the beginning of the simulation, starting off with the foundation. So here we have a 20-meter deep hole, which is what we believe they would have had to have tried. And then we're just playing through now, each level going up.
Carl's modeling software simulates how the masonry monster behaves under real-life conditions.
And then here we've got the gravity load going on. These red areas here are showing where the stresses are highest. At the base here, also at the sides of the arch here. This is where the masonry is working really hard, and straight away the foundation starts to sink this side more than that side, and this causes the tower to lean over, and these very high stresses developing on this side, and now we've got a hinge developing, buckling of columns, parts falling out, and catastrophic collapse. It's hitting the ground, and a mini earthquake really, which is what's happening here. Eventually settles down as a pile of rubble.
Carl proves that Eiffel was right. A stone tower this tall is a really bad idea.
It weighed 150,000 tons, we believe. If they'd have kept going, it would have done that.
Eiffel wins the argument. He convinces the judges that iron is the material for their tower. It will make the tower not just strong, but very light, as engineer Ed McCann reveals.
Of course, wrought iron is a metal and it's really heavy. The way it's put together on the structure results in the whole thing being really, really light. In fact, if this was the real Eiffel Tower and I had a glass big enough to drop over it like that, the air inside the glass would weigh more than the structure itself.
Having won the competition, Eiffel now faces a formidable challenge. He has only 2 years to forge 18,000 pieces of iron and assemble them accurately. To make sure the tower doesn't lean, he must line up the 4 heavy legs precisely. Engineer Jem Stansfield shows how Eiffel did it with an ingenious invention called a sandbox.
This is my model of the Eiffel Tower. These are my legs. This one's slightly more vertical than it should be, and supporting it is a sandbox. Now, that is just a box with sand in it, a plunger in the top, and a hole underneath that can be opened up to let the sand out. See how it goes. Now what Eiffel did was let the sand drain out of the sandbox. You've got to be careful because you can't pump it back up. But he could make this almost a grain by grain operation. Just drifting into place. Nearly there, nearly there. Yes. Now, I've got these 2 legs level. Imagine once he's got all 4 legs level, he's got the perfect platform that he's after. This is almost primitive, but it's absolutely ideal for the operation that Eiffel had in mind.
It takes Eiffel over a year just to build the 4 legs. He soon finds himself running out of time.
By March 1888, construction's reached the first stage, which is where I am now, which leaves them 1 year to complete the other 2 stages and top out the tower.
Riveting together thousands of iron girders high up on the tower will take a lot of time. But Eiffel has planned ahead. His crews will do most of the riveting on the ground.
They brought these sections to site largely completed, and only a third of the rivet connections had to be made here. There are 2.5 million rivets in it and 18,000 pieces of metal, and yet only 130 people actually worked putting it together. This was extraordinary.
Eiffel transports the prefabricated sections from his factory to the site on the left bank of the Seine. Then he uses steam-powered winches and cranes to hoist the gigantic pieces up the tower. On the highest section, he couples 2 cranes back to back so the weight of one counterbalances the other. Jacks lift the cranes up the tower as it rises. Step by step, the tower climbs higher and higher. And once the tower is complete, Eiffel cleverly adapts the crane track to carry the lifts. Thanks to his climbing cranes and streamlined assembly process, Eiffel meets his deadline.
March the 30th, 1889, and the workers were done. They had finished. Here we were at the top of the Eiffel Tower. The very next day, Gustave Eiffel led a team of dignitaries all the way up the 1,710 steps right to the top to show them something they'd never seen before. Paris from 1,000 feet.
Like Gustave Eiffel 100 years ago, the architects of the Canton Tower are determined to create a building unlike any other. Conventional TV towers are shaped like tall needles with circular observation decks. Mark Hamel's vision is radically different.
Most observation towers, I always call them donuts, because they are like spikes with a donut pushed from the top. If you then still want to do something new, then you have to think, how can you change that pattern? The tower is actually based on a very simple idea, which is just like 2 circles or maybe ellipses that are connected with steel columns. The next step is then to take these 2 circles and like rotate them against each other. So then by some kind of surprise you get like a waistline appearing.
Here you can see the effect the rotation has on the actual waist. So see, if I'm turning this, that it becomes not only much more narrow in the middle, but you can also see that the columns are actually closer together.
Turning this radical design into reality will be a challenge for the engineers. To achieve the supermodel look, they must combine the strengths of concrete and steel. At the heart of the tower, they'll put a hollow concrete column to house the lifts and stairs. From this, they'll suspend 5 modules containing floors of equipment and observation galleries. To brace this concrete core, they'll wrap it in steel columns. This gives their tower the desired shape. But the narrow waist is a weak point where the tower could buckle. Engineers fear that such a unique tower will be very difficult to build.
The engineers were, in the beginning particularly, they were quite skeptical because of the fact that it first narrows down and then becomes wider again. So it is almost like very illogical.
The thin waist is an architect's dream and an engineer's nightmare. Mark is confident. He's seen a design like it before.
I'm very much influenced by kind of like natural objects, and I'm particularly looking at microscopic photos of, for instance, like a bone structure. I think because it's very similar to the job that a very tall building has to do.
Like the tower, the human thigh bone is wide at the ends and narrow in the middle. But the walls of the bone are much thicker in the middle to give it more strength.
You can learn a lot of tricks from nature, which is making it denser, like the structure denser where it needs to be dense because it needs to be stiff, and making it lighter and taking more material out, basically at the bottom and then at the top.
The engineers add steel rings inside the columns to tie them into a strong lattice. And they concentrate the rings at the narrowest part to give it extra strength, like a thigh bone. The result, a tower with a narrow waist that's rock solid. The Canton Tower is made up of over 4,000 different pieces. To assemble them, the engineers borrow some tricks from Gustave Eiffel. Like him, they use cranes to lift the metal pieces up the tower and swing them into position. Workers then bolt and weld them together into a seamless steel skeleton. And just like Eiffel's crew, they jack their cranes up the building as it rises. Without Eiffel's ingenious ideas, building this tower might not have been possible. In just 23 months, the Canton Tower rises 610 meters above Guangzhou. Despite the engineers' fears, the narrow waist is a triumph, elegant and strong. An open staircase winds its way around it, so visitors can feel the wind in their hair. The views are stunning, and there's not a donut in sight. Back in 1889, Gustave Eiffel shows the world that lightness is the key to building tall. But as towers grow ever taller, they have to battle a new enemy: the wind. When the city of Toronto in Canada decides to build the tallest structure on Earth, they must make it strong enough to withstand the onslaught of the elements. In the 1970s, the city of Toronto has a problem. The skyline is teeming with skyscrapers that disrupt TV signals. So the city needs a taller antenna. They decide to go for glory and build the tallest structure on the planet: the CN Tower. But the builders face a formidable foe: the wind. As the tower's engineering director, André Secker, explains.
We are getting a speed of about 10 to 12 kilometers an hour, and we will go up there to see the difference between up top and what it is here.
Wind can be harmless at the bottom of a tower, but turn really vicious at the top.
44 kilometers an hour. Well, it's not that bad, but it's extremely windy. The maximum speed that we measured since the tower has been built, it was about 120 kilometers an hour.
Winds travelling at such speed can push on a tower with a force of several thousand tons. To help the CN tower take the strain, engineers will build it with reinforced concrete. They'll assemble a huge concrete casting form 3 stories tall. At the top, workers will pour in concrete, which will run into a mold below. As the concrete hardens, hydraulic jacks will lift the form and a flawless tower shaft will emerge. On a good day, the CN tower will grow a whopping 5 meters. Concrete alone won't be able to withstand Toronto's winds, as Jem Stansfield explains.
Concrete's a wonderful building material, and it's been successfully used for 1,000 years, but it has a major weakness. This is obviously a tower of bricks, but it behaves like a tower of concrete in an exaggerated way.
The bricks represent the microscopic layers in a concrete tower. Now Jem simulates a gust of wind hitting the concrete.
And what happened there was the building experienced a side load, and under those circumstances it wants to bend. And bending means it gets crushed on one side and stretched on the other. And with a concrete type tower, that stretch side begins to crack and fail.
Jem tries to make his tower stronger by tying the bricks together with steel rods.
These steel rods on their own are pretty weak. The bricks are pretty weak as well, but the combination could be something special. I'm now going to give it everything I've got to try and knock it down. There you go. A fine shot that would normally take down any stack of bricks, but these, they're just not going to come over. And it's that combination that does it. The steel taking the tension and the concrete taking the compression.
Mix of steel and concrete becomes the key to the CN tower's strength. At set levels, workers will thread steel cables through the concrete shaft and feed them down to the basement. Here, hydraulic jacks will pull the wires tight and anchor them to the foundation. The tower will need nearly 1,000 kilometers of steel tendons to stop it bending in high winds. Work on the concrete core of the tower starts in 1973. To keep on schedule, workers carry on through Toronto's bitter winter. But as temperatures plummet to minus 18 degrees Celsius, the builders hit a serious problem.
If the concrete freezes, that can cause the binding would not take place between the cement and the gravel.
To stop the concrete from crumbling, the builders have to keep it warm.
So basically what they did, they set up a plant at the base of the tower where they mixed the concrete, and they had to actually heat the water to 57 degrees Celsius. They heated the sand to 55 degrees Celsius to ensure that the work temperature is good for the concrete to bond.
To shield the warm concrete from the icy winds, they hoist it up in buckets inside the tower core.
And we had propane heaters inside the core to make sure that it's heated to avoid the concrete freezing.
As the tower rises, workers thread the steel tension cables down the concrete walls to the foundations. Their anchor points are still visible in the basement today.
We ran basically these tensioning cables all the way to the top through the conduits, and we terminated the cables at the base of the tower. We are using the tensioning cables to stiffen the building against maximum force wind, and so the concrete does not crack down under these forces and under its own mass as well.
To top out the tower, the builders draft in a huge Sikorsky helicopter called Olga. She delicately stacks the 44 pieces of antenna on top of each other. In March 1975, she places the final segment and secures the CN Tower its place in history. For over 30 years, it will remain the tallest structure in the world. In China, the Canton Tower, with its narrow waist and extreme height, appears vulnerable to the wind. But it has a special design feature that helps it defy nature's blasts: its shape. As strong winds pass over a conventional tower, they create spirals of wind called vortices. These pull the tower sideways and can take it to the brink of collapse. But the irregular twisting shape of the Canton Tower disrupts the vortices, reducing the sway. And because the outer lattice of the tower is open, the vortices break down even more, so even strong winds cannot grab hold of the tower. Although the tower's open structure protects it from wind, in Guangzhou it faces a particularly fearsome enemy: the typhoon. Every year, devastating storms wreak havoc in the region. Winds hit top speeds of over 200 kilometers per hour and can easily topple a tall building. But the Canton Tower has an anti-typhoon weapon hidden right at the top. 2 huge tanks filled with over 100,000 liters of water. To show how they protect the building from wind, Jem Stansfield has built a mini tower from spaghetti.
With any structure, it has a certain level of flexibility and a certain mass. Here's a bit of mass. Now when the wind comes in, it can cause a building to oscillate. If that oscillation is around about the natural frequency of the building, you've got a problem. Potentially a huge problem.
Over time, this tower will break. Jem tests a second model, filled with liquid at the top.
Let's see what happens. That's simply astonishing. This one is swaying to a point that it's really bound for catastrophic failure. And this one is almost steady as a rock. And it's because this liquid sloshes around at the top there in such a way that it comes up against the sides and counteracts the sway of the building every single time. Simple, but brilliant.
The water tanks of the Canton Tower, known as dampers, can move from side to side on a system of rails. In strong typhoons, the tanks can shift over a meter, absorbing the wind's energy and keeping the tower stable. The tanks ensure that diners in the restaurants can sip their wine without spilling a drop. Back in the 1970s, the CN Tower shows that even record-breaking towers can survive nature's fury. But today, as super towers reach the dizzying height of over 600 meters, new challenges emerge. The Canton Tower needs cutting-edge technology to keep people safe inside it. Midday on the 27th of August 2000. Television screens go blank all over Moscow. A fire has broken out in the Ostankino television tower. The blaze rages through Europe's tallest building, blocking access for the firefighters. 4 people die trapped inside the tower. The tragedy reminds engineers that a tall, thin tube is a bad place to be during a fire. The Canton Tower in Guangzhou receives over 8,000 visitors every day. At any time, several hundred people can be milling around the observation galleries high above the ground. To protect them from the dangers of a fire, the tower has 3 layers of defense. At the top of the tower, the large damper tanks feed water down to an amazing innovation. Robotic firefighters that guard the lobbies. At the manufacturer's test facility, engineers put the system through its paces. As the blaze roars up from the warehouse floor, the robot's infrared sensor spots it within seconds and takes aim. Bang on target, the powerful jets exterminate the fire. When the robot senses that the fire is out, it turns off the tap to prevent excess water from damaging the building. Fighting fire is the first step to safety. But fire itself isn't always the biggest threat to a building.
During a fire, smoke is actually the biggest problem. That's why these lobbies in front of the list are pressurized, as is also the staircase.
Visitors must be able to escape from the public areas into the stairwells in the tower core. So the tower's second line of defense is smart ventilation. Jem Stansfield demonstrates with a simplified model of the tower.
One way of keeping smoke out of stairwells and important exits is to blow air into them. Now what I've got here is a model to represent the Canton Tower. This is a stairwell and these rooms coming off it. Now in a fire, the last thing you want is an exit like this choked with smoke. I'm going to do just that now. And there you see the smoke's just hanging there, and it would make it very difficult for an evacuation to happen. So what they do is blow air into it. And you can see immediately the smoke is clearing out of the stairwell. The vital thing is to get this clear as soon as possible. And there we go, that's cleared up really nicely. These are still a bit choked, but the important thing is people can now get out of the building. Now this works so well because the blower actually increases the air pressure ever so slightly in this exit area, which means any smoke and fumes in it start moving out from it, but more importantly, any fumes being created elsewhere in the building can't feed into it, so the exit stays clear.
The core of the Canton Tower has long ventilation ducts running down along the emergency staircases. If a fire breaks out, powerful fans suck in air and blow it through the ducts into the staircases. This pushes smoke out of the core to keep the escape route clear. The stairs lead people to the third layer of protection, refuge areas scattered through the building.
On top of each block is a space like this. People take a staircase down to this refuge floor, and from here they can be rescued by firemen that can take them all the way down.
These features make the Canton Tower safe, even in a fire. Like all its mighty ancestors, the Canton Tower has pushed the frontiers of engineering and tapped into humankind's love affair with tall buildings. It's designed to thrill with the sheer excitement that comes from being up high. For now, the Canton Tower is the tallest tower you can visit. Until someone builds an even bigger one.